statistics from other types of statistics that maybe you have come across in your, especially undergraduate education. So these ideas are very good to know, but after a little while they will not mean anything because somehow they're all common sense. Okay, but we need to review them, and I do provide in the slide some notes on other type of statistics you may have seen before, but intentionally I'm not going to discuss them during the lecture. Okay, so you can read them because they are important to understand why we do what we do, but I don't see a point of us discussing it, considering we don't have much time. So if time allows, and I hope it does allow, I want to discuss in some detail the exponential family of distributions. And we need to discuss it not only because it's important, but also because your homework contains something about the exponential family of distributions. So I will do maybe the homework today, sort of, okay? But I want to do some more advanced calculations if time allows. All right, this is the Reverend Thomas Bayes that wrote a single paper that has revolutionized basically information sciences. So when I was in visiting the University of Edinburgh in May, they're building some new institutes on data sciences, and everywhere they had his picture with the label "our former graduate." And it's like, give me a proof that this guy was a graduate of the University of Edinburgh. But obviously a university with a long history, right, can claim that. So they claim that he passed from Edinburgh. I suppose everybody does, one time or another, right? I did too. All right. So we're going to be doing a lot of jumping. This is my jumping sort of indicator here. So we're going to go to slide 9. And so let me start with the bottom, something you already have seen. There's nothing strange about this. So let's consider maximum likelihood estimation of the mean and the variance for the Gaussian. By the way, I realize the pointer never comes across on the videos, so I need to point at least or say something which equation I'm referring. So let's say that we have n samples from a Gaussian, univariate Gaussian, and we want to compute the mean and the variance using maximum likelihood estimation. So when you do all the calculations the way that you see on the bottom equation, this is the likelihood for a single sample. You take all of this to be independent for all the samples. You do the calculation, you put the product inside an exponential, you get a summation, and effectively you get what you see on the bottom. Common sense derivation, there's really nothing to it. But what I want to remind you in this calculation, first a notation theta. Theta 1 is mu and theta 2 is sigma squared, just to simplify the notation here. But you notice in the likelihood, you do get all the data coming in two simple scalars. One is the sum of the xj's, and another one is the sum of the xj squares. So we call this two terms the sufficient statistics for the estimation of theta. Can you see why the name sufficient statistics? What does that mean? So, maximum likelihood estimation, right? We're going to compute theta by maximizing this, and we say we will call this the sufficient statistics. So what does it mean? Common sense language here. Remember, time is gold. I have time, but every slide will be 30 seconds, so your answer has to come in 10 seconds. So what does it mean that these are sufficient statistics before we formally discuss it? I mean, how do you understand it? Because if it makes sense as a common sense definition, then we're okay. Why we call this sufficient statistics? There is no distribution here. We want to determine theta. So why, for the determination of theta through maximum likelihood, we call these two summations the sufficient statistics? because the only way that the data come to affect the evaluation of theta in this function is through these sums. You see that? It's not like every term comes individually in some strange way. Is at the end of the day, if you have n data points, this summation is what defines theta. So basically, as the data comes, I can get rid of it and say, look, I only keep track of these two summations because alone they can define the maximum likelihood estimate. We agree? All right. Now, I am going to try to generalize the concept of sufficient statistic, right? But I am not going to do a good job here because it requires some knowledge that maybe we mentioned a few things on conditional independence in one of the earlier lectures. But let's consider that we have some parameters theta that we want to compute. This is what I just defined as sufficient statistics of the data x, and this is the data x. So the way that we introduced it with a common sense language was that P of x is everything I need to know to compute theta. All right? So, so if somebody gives you another information about x, it is not relevant for the calculation of theta. But in the way that I have it here vectorially, it basically, this picture, and we will learn more of this in another course, it basically says that if I give you the sufficient statistics, so if I give you those summations, x and theta are conditionally independent. Right? So basically x doesn't depend on theta given T of x. So if you know T of x, you don't need to know anything about x to relate that to theta. T of x contains all the information about theta. Now somewhere in an earlier lecture, I gave you a decomposition which I also proved it using this independence relation, and it says basically that my likelihood here, you can accept this as is, all right, so that I don't have to elaborate a lot, is basically some function of T of x and theta times some function of x and T of x. And in this particular case, these are conditional probabilities since I use this directed graph. Okay, so again, with the definition of the sufficient statistics and the independent statement that I mentioned, that given T of x, x and theta are conditionally independent, you can factorize the likelihood, the probability of x given theta, as, in this case, a function of T of x and theta, and a function of x and T of x. Okay? This is very important. Okay? It tells you that theta comes in one function together with T of x, not with x. Maybe you don't remember, but somewhere in the slides on conditional independence, I did mention that conditional independence leads to some factorization that looks like this. So you may want to go back and look at this at an earlier slide. Okay. So in our Gaussian, these are the two terms. It is important to note that they're scalars. So the data can be an infinite number of data, n can be huge, still the sufficient statistics are scalars. This is very important. So, are they unique? Of course not. For example, I can scale this thing, divide by n, or I can use this. My data variance. These are also sufficient statistics, and I can write things in terms of the sample mean and S square. So, but more or less, these two variables define my sufficient statistics for the estimation of mu and sigma squared. Okay, we jump to slide 12. And let me just put a few things up. So I would like you to guess now what the sufficient